Okay, so I want to talk to you a little bit about graphing square root functions. Now I went ahead and made a t-chart of a quadratic function, y equals x squared, and also a square root function right next to it. And I made inputs and outputs for both so you can compare them. For y equals x squared, I have x equals 0, 1, 2, 3, and then the y is 0, 1, 4, 9. And this is something we studied before. And there's the 1, 3, 5 pattern that we used for graphing the parabolas. Now take a look at these x values I used here. Well, I decided to use perfect square values because those are easy to plot. Because the square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. Now with these y values, there is no 1, 3, 5 pattern here. It just goes 1, 1, 1. But look at the x values. Right here it goes 1, and then 3, and then 5. So the 1, 3, 5 rule, it does apply to a square root, but it applies to the x's and not to the y's. And really what happens here is the inputs and the outputs were switched. Notice how the x's here are now the y's, and the y's here are now the x's. And that's because these two functions are called inverse functions. They're inverses of each other, which means you switch the x and the y. And it also means the graphs are related, but not exactly the same. So I'm going to go ahead and plot the y equals x squared first. So I'm going to use the 1, 3, 5 rule to plot this. 0, 0, then over 1, up 1, over 1, up 3, over 1, up 5. And then, of course, we reflect the points through the axis of symmetry. And then the parabola goes like this. Okay, so that's y equals x squared. Now let's take a look at y equals square root x. So I'm going to plot the points as shown. 0, 0, 1, 1, and the next one is 4, 2, so 4 and then 2, and then 9, and then 3. So here are the points that are from the table. Now what happens when x is negative? If you try to put a negative number in here, a negative number is not defined in the square root function, at least not in the real numbers. So square root of negative anything, you can't get an output for. Which means the graph kind of just starts at 0, 0. There's nothing else to the left. And then you just connect it going to the right. So it's like that. Now looking at these two graphs, it's almost like you cut the parabola in half, and then you just take this first piece, the piece on the right here, and then you reflect it through the line y equals x, a diagonal line right here. Okay, so this is like a reflection line. And this is true of inverse functions, that you're going to have a reflection through the line y equals x, and that's because the inputs and outputs are switched. So you're switching the x and the y values. Now for our purposes, for doing a quick graph of a square root function, you can apply the 1, 3, 5 rule. And let me show you a couple more examples. Okay, let's say you have y equals 2 square root x. Here's a t-chart, 0, and then square root of 0 times 2, that's 0. 1, input of 1, square root of 1 is 1, 2 times 1 is 2. The next one is a 4, the next perfect square root of 4 is 2, and then 2 times 2 is 4. And then the next one is 9, so square root of 9 is 3, 2 times 3 is 6. Now look at what happens here. We have 2, 2, 2, and then here we have 1, 3, 5. So what this 2 does is it creates a difference of 2 between the y's when we're using perfect squares for inputs, but the 1, 3, 5 rule is still the same. So let's show you what happens when we plot these points. We have 0, 0, and then 1, 2, and then 4, 4, and then 9, and then 6. Okay, so this one, it still dead ends at 0, 0, and then it continues to the right, kind of like that. So let's look for some type of a 1, 3, 5 pattern here. So 1 and then 2, 3, 2, 5, and then 2. So this 2 in front of the square root x, what it does is it changes how high you're going. You go 2 each time, and it's 1, 3, 5 going to the right, which is the reverse of the parabola. Remember, the parabola was 1 and then 3 and then 5 going up. Okay, let me show you another example. Y equals 4 square root x. Make a t-chart, x and y, 0, 1, 4, 9, still using the perfect squares as inputs. And then the first output, square root of 0 is 0, 4 times 0 is 0. Input of 1, 4 times 1 is 4. Input of 4, square root of 4 is 2, 4 times 2 is 8. Input of 9, square root of 9 is 3, 4 times 3 is 12. So we'll go with 0, 0, and then 1, and then 4, and then 4, and then 8, and then 9, and then 12. So this one go like this. And this y equals 4 square root x. And look at what happens. Over 1 up 4, over 3 up 4, over 5 up 4. So this 4 changes how high up you go each time, and it's still the 1, 3, 5 going to the right. Now if this pattern is a little too complicated for you, making a square root graph, you can easily just use the perfect squares each time, at least when it starts at 0, 0. And then you can just go ahead and plot the points and draw your graph. Now what happens if you're not starting at 0, 0? Let's say you have y equals square root of x minus 2 and then plus 1. Well, let's see what happens. If I try to input a 0, I get 0 minus 2, which is negative 2, and then square root of negative 2 is undefined. So 0 is not in the domain of the function. To find the domain, what you can do is you can say that x minus 2 has to be greater than or equal to 0, because we know the square root function inside that symbol has to be greater than or equal to 0. And then if I add 2, x is greater than or equal to 2. So here's my domain of the function. I know 2 is the smallest value. So let me input a 2. 2 minus 2 is 0, and then 0 plus 1 is 1. So on my t-chart, x and y, 2 is my first input, and then 1 is my first output. Now what if I input a 3? 3 minus 2 is 1, and then square root of 1 is 1, and then 1 plus 1 is 2. So if I input a 3, I'll get a 2. What if I input a 4? Well, 4 minus 2 is 2. Square root of 2, that's a decimal like 1.4 or something like that. And then plus 1 is 2.4. This is going to get a little messy with the decimals. You can continue this way if you would like to. But you can also apply the 1, 3, 5 rule. So here's how that works. I'm going to start at this 2, 1. So 2, 1, that's right here. So that's going to be my first point. And then I'm going to go over 1, up 1, over 3, up 1, over 5, up 1. Now the reason why I go up 1 each time is because there's an invisible 1 in front of the square root symbol. If there was a 2, I'd go up 2 each time, but I always go 1, 3, 5 to the right. So let's look at these coordinates. We have 2, 1, 3, 2, and the next one is 6, 3. And let me just check that. I'll input a 6. 6 minus 2 is 4. Square root of 4 is 2. 2 plus 1 is 3. So 6, 3 is on there. And this next one, see, that's 2, 4, 6, 8, 10. Looks like 11. And then 4. Let's test it. 11 minus 2 is 9. Square root of 9 is 3. 3 plus 1 is 4. So 11, 4 is in the function also. So if you're not at 0, 0 for a starting point, this 1, 3, 5 rule can help you out a lot. It really helps you find the integer points and makes the graphing easier. So once again, if you're not starting at 0, 0, try to use this 1, 3, 5 rule going sideways and see if that helps you as far as creating the graph more easily. And finally, talk about domain and range. We figured out the domain is x is greater than or equal to 2, and the range, well, that's the y values, and from the graph, y equals 1 is the smallest point, so it's y greater than or equal to 1. And that's found from this value right here. So it's going to be y greater than or equal to this number after the radical symbol. So that completes my explanation on graphing square root functions.